When you step into a critical power facility, the digital interface, the HMI, is your primary tool for gathering evidence. It tells you what the system is doing right now. But let's be clear from the start. Safe operation relies entirely on physical procedures and verification. You are dealing with massive industrial switchgear and parallel UPS cabinets humming with latent energy. A single operational error here carries massive stakes. This training bridges the gap between the physical reality of those power flows and the digital data displayed on your screen. You need to know exactly what the interface is telling you before you operate, test, or troubleshoot. The absolute first rule of system diagnostics is identification. Before you touch a single button, you must physically match the selected interface screen to the exact piece of hardware standing in front of you. You have to know its role in the room. Parallel IT UPS units work together to serve a common critical load, while mechanical or auxiliary UPS units operate independently to support facility infrastructure. Never assume that parallel units share the exact same operating state, active alarms, or battery conditions. One unit might be perfectly healthy while its partner is compromised. If you read data from one unit and apply it to the physical switching procedure of another, interface telemetry goes from being a helpful tool to an active hazard. Effective HMI interpretation begins with an exact understanding of the facility's power paths. You must be able to trace the flow from source to load before reading specific values. Look at this diagram showing the normal online power path. Energy flows from the utility source, through the transfer switch, into the rectifier, across the DC bus, through the inverter, and finally out to the critical load. The static bypass path is entirely separate. It bypasses the UPS electronics to supply the load directly. Because it skirts the inverter, it offers significantly reduced conditioning and protection for that load. Connected to the DC bus is the battery system. It serves a dual function, discharging stored energy to support the bus when the main source drops, and receiving charge current from the rectifier to restore its capacity. Finally, we have the purple dashed lines representing the battery management system and monitoring connections. These are exclusively data pathways. They report status and alarms, but they do not carry electrical load. Every digital value you read on an HMI screen is simply a sensor reading pulled from specific nodes along these distinct physical paths. You cannot safely interpret a voltage drop, a current spike, or a new alarm without knowing exactly which power or data path is currently active. Random navigation through interface menus leads to context-blind decisions. To prevent this, you must follow a strict, fixed mewing sequence, starting the moment you look at the home screen. Run through this mandated visual checklist every time. Verify the selected equipment ID, confirm the operating mode, check the active alarm count, and note the battery indicator. The operating mode defines how power reaches the load. In online mode, the inverter supplies conditioned power while the battery floats. Contrast that with battery mode, where the main source is lost and the battery takes over the DC bus. Static bypass means the load is fed directly from the bypass source. You will also see alternative states. Generator-supported operation means the UPS is bridging a source disturbance until the generator stabilizes. Be incredibly cautious with eco, green, or sleep efficiency modes. They deliberately expose the load to source anomalies to save energy. They do not offer the same protection as normal online operation. Before you take any control action, execute this 6-step inspection. Identify the unit, confirm the mode, check the alarms, review the input, review the output, and review the battery. Establishing this high-level context is the mandatory prerequisite before you drill into granular measurement data or authorize any maintenance. Once you establish context, move to the measurement menu. This is the evidentiary core of the interface. It answers two critical questions. Is the source stable, and is the load protected? On the main input screen, verify phase voltage, line voltage, current balance, and frequency stability. Frequency is especially critical during generator operation to ensure the source is stable enough to support the rectifier. Check the bypass input screen next. A bypass source can be physically present but still unsuitable. You have to confirm synchronization and frequency before even considering a transfer. Next, differentiate between the inverter and the output. Inverter output confirms what the power electronics are internally generating. UPS output shows what the physical load is actually demanding. Look at this power triangle to understand the load demand on the output screen. The x-axis represents kilowatts, the real power consumed by the load. The hypotenuse represents kilovolt amps, the apparent power capacity demanded from the UPS. The angle between them dictates the power factor. On the power module summary screen, check for balanced current sharing across all active modules. A single unbalanced or faulted module compromises the entire system's redundancy. These telemetry screens provide the electrical evidence required to justify a load transfer, test, or isolation procedure. A common operational error is relying on the basic battery icon on the home screen. That icon is a visual shortcut, not a diagnostic tool. You must open the UPS-level battery status screen. Pay close attention to current direction. Positive or negative values will tell you if the battery is charging or discharging, depending on the active mode. You also need to distinguish between state of charge, which is the current usable energy remaining, and state of health, which measures the battery's degraded condition against a brand new baseline. Understand that the displayed runtime is never a guaranteed duration. It is a highly volatile estimate dictated by live load swings, ambient temperature, and battery age. Because of that volatility, the UPS interface alone is not enough. You must transition to the Battery Management System, the BMS. This is the absolute diagnostic authority for energy storage. The BMS monitors a specific physical architecture. Individual battery cells are wired in series to build the required DC voltage. Those strings are then wired in parallel to build capacity and redundancy on the main DC bus. At this granular level, the BMS measures exact parameters the UPS misses. It flags delta cell voltage imbalances, internal resistance degradation, and localized maximum temperatures. Watch how an alarm propagates. A critical thermal event at an individual cell cascades up, triggering protective contactor trips and pushing a generalized battery warning to the main UPS interface. This creates a rigorous cross-checking mandate. You must habitually verify system-level UPS summaries against the granular, cell-level evidence buried in the BMS. Executing a high-risk switching maneuver based on a generalized UPS battery summary without investigating the underlying BMS data is a direct path to a catastrophic facility drop. The setup menu is restricted territory. The parameters found here, like voltage thresholds and string counts, control how the system reacts to faults. They dictate the protection logic itself. When diagnosing a fault, the event log is your primary tool for root cause analysis. While the active alarm screen shows immediate status, the event log allows you to reconstruct the exact timeline of historical events leading up to the failure. During a startup sequence, the interface serves a very specific purpose. Use it strictly to confirm source availability, rectifier readiness, and inverter stability before any physical breakers are thrown. Maintenance bypass operations carry extreme risk. You have to confirm source synchronization and bypass health on the HMI before exposing the critical load to the raw utility feed. The interface also tracks your stop criteria during testing. Load bypasses require monitoring inverter capacity and thermal limits. Battery discharge tests require tracking the lowest cell voltage and delta spreads on the BMS. The digital interface confirms readiness and logs results, but the execution of these high-risk operations is governed entirely by the approved physical procedure. When things go wrong, stick to a disciplined troubleshooting sequence. Identify the unit, confirm the mode, read the active alarms, review the history, check the measurements, and cross-reference the BMS. Use a symptom-to-screen approach. If you have an output overload, go straight to the UPS output and power module screens to verify phase balance and module redundancy. Let the specific fault dictate your digital investigation. Never prematurely clear alarms or reset statistics. You must record the evidentiary timeline and get authorization before wiping the very data you need to find the root cause. Finally, we reach the do not proceed safety checks. These are the absolute hard limits where you must halt all operations. Stop immediately if the selected unit is ambiguous, the operating mode is misunderstood, the bypass source is out of tolerance, or the digital state contradicts the physical breaker positions in the room. The interface grants visibility and diagnostic evidence, but never permission. Safe intervention always requires authorization, physical isolation, and adherence to approved procedures.